Welcome back. We're now going to embark on nucleophilic additions that involve oxygen nucleophiles other than water. And right out of the gate, you probably already guessed that oxygen-based nucleophiles, aside from water, are probably going to be alcohols. And basically, any type of alcohol will do the trick. We could have something as simple as methanol. We could have something a little bit bigger, like ethanol, still simple. Isopropanol, tributanol. So in reality, it doesn't really matter if the alcohol is primary, secondary, tertiary. They all can do the nucleophilic addition because these things are not the substrate, but rather the nucleophiles. You could also have aromatic alcohols such as phenol, but you could also do reactions using molecules that contain two alcohol subunits, also known as diols. So ethylene glycol will be one of them. This derivative, this ether derivative as well, that has hydroxyls on the end, alcohol subunits. You could also have aromatic alcohols that happen to be diols, such as naphthol, shown here, 2,2 prime naphthol. And we're going to see how these molecules react with your typical aldehydes, your ketones. All right, so we're going to do a reaction under acid catalyzed conditions with a simple alcohol. And the product that we're going to generate, that's known as a hemiacetal. So we're going to show you how that happens. All right, so under acid catalyzed conditions, the first thing that needs to happen is protonation of the carbonyl. So this is no different than what we did with water. Now, the only difference is that we're not doing this in the presence of water, just alcohol. So the thing that's protonated, obviously you'll add HCl or sulfuric acid, something that's strong enough to donate a proton. And that proton could be donated to the alcohol or it could be donated to the carbonyl. But to show the process, we're going to have it present on the alcohol, kind of like hydronium. And that proton is donated now to the carbonyl. The carbonyl attacks the proton, the electrons go back to the oxygen, reforming your alcohol. And then, just like we said before, the protonated carbonyl has the following resonance structure that makes the carbonyl carbon a lot more electrophilic than it would have been otherwise. So the nucleophilic attack now takes place with a molecule of the alcohol itself. So ethanol, which is the alcohol I just chose to do this reaction with, attacks with its oxygen lone pair of electrons, attacks the carbonyl carbon specifically, and then the pi set moves over to the oxygen to give rise to a neutral hydroxyl unit on the main chain, but now you have what used to be ethanol bound to that carbonyl carbon, making the oxygen positively charged. All right, so as you can see, right, acid catalyzed conditions, the substrate is either neutral or it has a positive charge. And that's kind of what we're seeing throughout this sequence. So the next thing that needs to happen is to remove that charge, make it neutral by having something remove the proton. Now, this could be, in this reaction, probably ethanol, but I'm using water here just, I guess, for space, for the sake of space. But technically, in your mechanisms, this probably will have to be methanol or ethanol, like we did right here. Now, the end result, as you can see here, is that you have reformed the catalyst, like we did in the previous case, but differently from before, now we only have one hydroxyl present on the same carbon. The other oxygen source is the alcohol itself. So you have an ether moiety, and then you have an alcohol moiety bound to the same carbon. This is what we refer to as a hemiacetal. So one alkoxy and one hydroxy group on the same carbon, you get yourself a hemiacetal. All right, and so you know the hemiacetal can be formed both under acidic and basic conditions. So it doesn't really matter how you start the process, you'll end up with this particular product. So let me show you how that happens under basic conditions. Pretty much you have to have the deprotonated alcohol, so ethoxide in this case. And there's various ways to do this. You can either treat ethanol with a stronger base, such as sodium hydride. You could even react it with an alkaline metal, which will produce hydrogen as a byproduct, but hydrogen is a gas, so it's gone. So you have ways of making this alkoxide relatively easily. And the alkoxide is a better nucleophile than the alcohol, just like hydroxide is better nucleophile than water. So this attacks the carbonyl carbon, kicking away the pi electrons towards the oxygen and forming these negatively charged intermediates. And since one of the basic conditions, the substrate, the organic substrate, has to remain either neutral or negatively charged throughout the process. Okay, so on the reprotonation event, you have one equivalent of your alcohol donating the proton to the alkoxide to make the neutral final molecule. And of course, what this means is that now you're going to generate an equivalent of etoxide, which is basically the catalyst or the base catalyzed conditions of this reaction. All right, so either way, we still have formed one alkoxy, one hydroxy group bound to the same carbons. We have formed that hemiacetal. So it works out the same way. And you can kind of see the similarities between this reaction involving alcohols and the one we did with water. In reality, there's really not much difference between them. All right, so the process can actually go a little bit further, specifically if you do this under acidic conditions. Because if you start with a hemiacetal, and assuming you have plenty of alcohol, which probably you would, because if you do this type of reaction, you're probably using the alcohol as a solvent. Under acidic conditions, there's one more thing that can happen. The hemiacetal can accept a proton from the catalyst, the acid catalyst that's present in solution. Just have the hydroxyl attacking the hydrogen, kicking away the electrons back to the positively charged oxo, the oxonium cation. And what this will do is now give you a water molecule that is basically a great living group to have. Now, this is something that's very interesting in respect to this hemiacetal business, because yes, you have a good living group just by having protonated a hydroxyl, but at the same time, on the very same carbon, you have another element with plenty of lone pairs. So pretty much you got a good living group and you got something that can donate electrons. So in very simple manner, the ethoxide group can donate electrons to ultimately kick away the living group, the water living group in the process. Now, what this is going to do, of course, is going to generate an oxonium cation for what used to be your ether moiety. And once that's formed, another equivalent of alcohol, and you got to remember, right? Yes, you have produced water in this second event, but if you're running this under solvent conditions where the solvent is ethanol, one water molecule versus a gazillion ethanol molecules is not even a competition. The chances that the oxonium intermediate we have here will react back with water, there is a possibility, but it's a minor one. So it is almost guaranteed that yes, you will undergo this reaction with the alcohol, attacking the carbonyl oxygen and kicking away those electrons back to the oxonium cation, making the ether moiety neutral. And now the alcohol that's present there bears the positive formal charge. Notice that throughout everything so far, the organic substrate is either positively charged or neutral. So the last event is simply that the proton that's present on that oxonium ion is removed by your solvent. And this event is, in essence, what reforms the catalyst that you started the process with. But notice that right now, you have two alkoxy groups bound to the same carbon. This is what we refer to as an acetal group or the acetal molecule. And this particular thing can only happen if you do this under acidic conditions. This will not happen under basic conditions. So if it is the case that you actually want to end up as your final product with a hemiacetal, you better not do that under acidic conditions, because you will bypass it and continue going to the acetal group if you have it under acidic conditions. But under basic conditions, you will stop right at the hemiacetal route. And that's simply because you don't have a good living group in the hemiacetal group to have an alkoxide, attack the actual hemiacetal. So keep this in mind. This will be important for later lectures. Now, on the next video, what I'm going to talk to you about is what happens when the alcohol that you're using happens to be a diol. So I'll catch you on that video. Bye bye.